Welcome to CPE214 Signals and Systems. I am Sanitam Prom-on. This is a backup video lecture of the third lecture, System Representations, Properties, and Block Diagram. Let's begin the lecture. Systems is an abstraction of a physical process. It processes the input signals and produces an output signals. So we can write it as this flow, that is, the input is fetched into the system and the system reacts to the input and responds with the output. So the term response and output are used interchangeably. You can use either of them to tell that this means the output. This means the output. We can represent systems in different ways. We can represent them in mathematics. We can represent them in graphical illustrations like in block diagram. And there are types of mathematics that we can use to describe systems. We can represent systems using differential equation as in classical methods. We can represent them as block diagram to represent the configuration of the systems. We can represent system as impulse response. That we will learn later when we simplify the system to linear systems. We can represent systems as its response to the frequency, and we can represent it as transfer function, which are the last three topics. We will learn them after. We will learn them later. I will use this notion, the arrow notion, to denote that this signal xt pass through the system, and then the system react to this signal xt with the output yt. So xt is fetched into the ct system because you can see that this is time index t, which means that the signal itself is continuous time. The system react with the output yt. Also note that the symbols that we used here can be replaced with different types of symbols like WT, ST, whatever. This is just to denote that there are some types of signals. So actually X can be the output and Y can be the input, and vice versa. For the discrete time systems, this tells you that signal Xn is fetched into the DT system, and then the system react with the output Yn. And I will also use this arrow sign to denote that Xn pass through the system, and then the system react with this input with Yn. Let's look at the first simple examples. To describe the system, we need to draw relationships between signals, between variables in the systems. In these systems, it is a basic electrical RL circuit. So you have a resistor here and a capacitance here. How can we derive relationships between signals? We can do that by using physical laws that are there. So here we know that there is a certain relationship between voltage and current. That is, the current here, the current IT passing through R, has to obey the Ohm's law. So IT equal VST, this source, and VCT, the voltage across C, over R. Then we can further substitute the terms into this equation. That is, we know that IT here, since it passed through the capacitor, also must obey the properties of the capacitor current. That is IT equal C, the capacitance, and dVct by dt, the change of the voltage Vt over time. So then we can equate the two equations by IT. Then we have C Vct by dt equal Vst minus Vct over R. Then by rearranging this equation, we have here RC dVct by dt and then Vst and Vct. So here the input, this voltage source, and the output, the current, the voltage across the capacitor. You can see that this equation contains only two variables. Two signals. One is the Vct signal. Another one is the Vst signal. So this is called differential equation. It describes the change in one variable with respect to the change in one variable, and given that you have relationship to the other variables. You can also describe relationship with something like this. That is, suppose that you have yn as a credit card debt at end month, and if xn denote your payment each month, xn denote your payment at the end month. Then suppose that there is a monthly interest rate equal 1%. Then you can write an equation like this. That is yn. This is the debt at the month end, and 1.01 yn minus 1 is actually the amount that you have, the debt that you have in the last month at the n minus 1, and we adding the 0.01, which is an interest rate, and minus xn, the amount you paid in the month end. And so this equation represent this debt situation, the systems, the finance systems. So you can see that there are two signals involved here: y, the debts, and x, the payments. Systems can be arranged in different ways. It can be put in the cascade manner. That is, the input of one system passing through system 1, you get an intermediate output here, and it is an input to the system 2, which produce the final output. The system can be configured as a parallel systems. That is, the same input is fetched into both system 1 and system 2, and then the output are combined later to get the final output. This is the parallel configuration. Or you can configure the system into a feedback style. That is, you take the output into one system and then compare it with the input, and then fetch the difference or maybe the addition to system 1 to produce the output. This type of systems can be found in many places, and there are many applications because they have the properties of stability. That is, the system can operate in a stable manner. For example, let's look at the air conditioner, an air conditioning machine. You give the air conditioner with an input, and then it compare the input with the output from what it get from the sensor. So system 2 is like a thermostat, and it gives you the measurement. When you subtract this out with what you want, you get the difference, and the air conditioner has to produce the cold air in order to get into the temperature into the level that you want. When we talk about the system in time domain, it can be represented by either differential equation or difference equation, as I just mentioned it. That is, the equation describes the differential relationships between input and output. Or the system can be represented as impulse response in CT term, or unit samples, which is also impulse, unit sample response in DT term. This impulse response describes the response of the system when the input is a unit impulse. We will talk about this in the next lecture. Let's look at this example of system representation using differential equation. This is the example that I talked earlier. That is, we can represent the air conditioning system like this. dCT, if we let RT and CT to denote the desired RT and the current room temperature. So the change dCT is the change in the actual temperature. Should be equal to minus some value, minus K, and this CT minus RT is the difference between the actual temperature and the desired temperature. The negative operator here is to denote that it should be decreased, because we are talking about Thailand. It's too hot, so the system has to try to cool down the room. So in this case, you can see that this equation represents the differential relationship between Ct, the output, and Rt, the input of the system. Now let's talk about the properties of the system. These are the list of properties that will be covered in this course. Note that there can be other types of property as well, which will not be covered. But let's look at this because these properties describe the kind of basic mechanisms of the systems. Some may be important to some types of system, while some may not be that important. First, let's talk about the system with memory or the system without memory. If the system relies on either previous inputs or output, then the system needs memories. In terms of programming, this means that the system needs to have some form of storage so that you can save like the data that you collected yesterday, then you will use those data today. That is something like the system that needs memories. But if a system does not rely on any previous input or output, then it is memoryless system. This is an example that this system's yn relies on the previous value of yn minus 1. Then this system requires to have memory. But for this system, yn equal xn squared, then you can see that the value of yn is calculated only based on the value at time n, meaning that something like the output at that has to be calculated today relies only on the data that you can collect today. That is the memoryless system. The system can be invertible if and only if when you have xt and you get yt, and there is an inverse system, that is when you have fetch it with yt, you get xt back. You can see that the system will be non-invertible if it has something like many to one mapping. For example, this yn equal xn squared. So you can see that the same value of yn may comes from two different values of xn. So this is non-invertible system. The system is causal if and only if the current output depends only on the current and previous input. Or in other words, if the calculation of the current output does not rely on any future input, then it is a causal system. So if we let xn and yn to denote input and output of input and output signals of the system can be causal if the current output relies on only current and previous input. It will be non-causal if the current output relies on something like it relies on the future input and maybe current and previous inputs. The system is anti-causal if the current output relies only on the future inputs like this. How do I know that it is current and it is future? You can just simply substitute the values of n with something like 0 here. If you're substituting 0 here, you have here equal 0 and this is minus 1. 0 and minus 1 are in the past. If this is 0, then you get x1 and x minus 1. x1 hasn't happened yet, so this is the future. For this yn, if n equals 0, then you get 1 and 2, all the future input. Be careful that if there is a scaling constant with this, you may need to test it with something else, like substituting 1 instead of 0 that I used. Having a causal properties doesn't mean that the system will not work, because in some cases you may end up with a system that is anti-causal or non-causal depending on the application. For a real-time system, like the system that needs to process the input online, like voice over IP, the system should be causal because the output should rely only on what you have in the current and the past, because it must react to the input immediately. While for something like archive processing systems, like when Google create a search engine, system can be causal, non-causal, or anti-causal, because there is no restriction on using the future values. Or if you want to predict the stock price, then you can gather the historical data and then create a model that use the future values or the next prediction to further predict the values of the current. The next property is stability. There are actually many definitions of stable. In this course, we will use the concept of bounded input and bounded output BIBO stability. The definition of this BIBO stable is that a system is stable if and only if the output is bounded for every input that it is bounded. So we can test it by first assume that the input is bounded. If the output is bounded, then you have a BIBO stable system. So here cos 2 pi t. Cos 2 pi t is bounded at -1 and 1. And this sin 2 pi t and the system produce the output e to the minus t sin 2 pi t. This is oscillated complex exponential. So you get a decaying complex exponential, decaying oscillation, which is also bounded to a zero value. So the first system is a BIBO stable system. For the second one, this is unbounded, e to the 2t, exponentially grows without bound. Although this is bounded, this system doesn't have, we cannot conclude that this system has BIBO stable because there is no bounded input to test. But for the last system, since the input is bounded and it produces the unbounded output, the last system is unstable. It's not a BIBO stable system. Now let's look at the last two important characteristics, time invariance and linearity. The system is time invariant, or we use Ti to denote the time invariant, if its characteristics do not change by time, meaning that something that you applied yesterday should also be applicable today. When you fetch an input to the system yesterday and it produces certain output, and if you fetch the same input to the system today, it should produce the same output. Mathematically, it means that the output of TI system should be the output of the TI system to the time shifted input is the time shifted output of the no shifted input. So if the TI system responds to the input xt with yt, then if you fetch an input, the shifted input xt minus capital T to the TI system, you should get yt minus capital T. For example, this system yn equal xn plus xn minus 1. If you fetch this input into these systems, you get this output. So when you fetch the same input but shifted instead of starting from 0 to starting from 5, you should expect something similarly, that is, it should be the same input but shifting the initial point to 5. So this should be y, the same y shifted by the same timing. For the not TI system, the characteristic may change by time, like it may occur from degradation for the equipment, or saturation if we are talking about a chemical process. So when you fetch an input xt to the system and you get the output yt, when you fetch the shifted version of the input xt into the system may react with different type of output. An example of non-TI systems. Let's look at this yt equal x2t. If we fetch this triangular signal as an input to this system, we will get a shortened version of the input because it's like running a video faster 2 times. So instead of spanning from -1 to 1, you get the output signal spanning from -0.5 to 0.5. But if we give the system with the shifted version of the same input by 11 unit, we should expect to have the same output shifted by 11 unit as well. But actually we wouldn't have that, because this signal will be scaled with respect to 0. So the starting point here would be at 5. The starting point of the output would be at 5, and the ending point would be at 6. The peak would happen at 5.5. So it's not the output shifted by 11 unit, just like in the TI system. The last property is about linearity. The systems can be linear or nonlinear, and most of the real-world systems are nonlinear. For example, if we are talking about the system if we want to describe the process of traffic flow to create something like Google Map to predict the traffic on the road, there can be a nonlinear elements in modeling that process. Something like if the car wants to take a U-turn, then the flow will change size, something like that. But usually nonlinear system can be linearized or simplified to a linear version. This process is called a linearization. This linearization makes engineers able to work to create a model that can predict and work with actual real-world systems. And this course will focus on these basic linear systems, so that further, when you have a nonlinear, you can simplify it to linear system and then doing something about it. The property of linearity is that if the system is linear, it should have a superposition property. What is a superposition property? Superposition property telling you that if you have a type of input x1 and you give this input into the system, you get the output y1. And if you have a different input x2, giving it into the system, you get the output y2. If you then combine them together and multiply them with certain values, constants a and b, and give them to the system, you should expect to have the combination of the output with the same scaling. For the DT system, it works in the same way, but with an index n instead. So my first question is this system linear? How will you know whether it is linear or not? You can use the same process as in proving whether the TI is linear. That is, first, let's assume that we fetch the system with the signal xn. Then you get yn equal y1n equal n x1n. If we give the system with an input x2n, then we get y2n equal n x2n. Then let's assume that we have x3 equals a constant multiplied by x1 and a constant multiplied by x2 as an input. If we give this input to the system, we get yt equals n x3n. Then this x3n would be equaling to ax1 plus bx2, and multiplying a inside, you get an x1 and bn x2. And this ax1n, if you look above here, you can see that this is y1n, and n x2n here is y2n. So this is a y1n and b y2n. This means that this system is linear because giving a small input to the system equaling to giving a big combination input to the system. So it's like when you give x1 a small input to the system, you get certain type of output. If you give the system with x2, you get another type of output, and then if you add them together and give the combination to the system, you get something like the combination of output. Then this system is linear system. Now this is the end of the third lecture. If you have any questions, don't forget to ask me on the Facebook group. I will respond it as soon as I can. See you next time.